Alright, so let us once again begin with a quick recap. So almost the entire lecture, last lecture we were looking at the bitwise MAP decoder. So let me just quickly recap about what I spoke about this decoder. Okay. So the essential idea is to compute what is known as the log likelihood ratio given the entire vector. Okay. So I think I might have called it vector log likelihood ratio or given the entire vector. So basically we want to compute probability that a particular transmitted bit is 0 given the entire received vector r divided by probability that the bit is 1 given the entire vector r. Okay. So log of this is the log likelihood ratio that you want to compute. Okay. So which we denoted capital Li for instance. Okay. So it turns out it can be written as some complicated expression which will essentially factor as Li plus some extrinsic LLR. Okay. So this Li is simply 2 times Ri by sigma square. You can think of it as the scalar or the channel LLR for the ith bit. Okay. So this extrinsic LLR of course is the key, right. The entire point of decoding or soft decoding is to compute the extrinsic LLR. The intrinsic LLR is just the channel LLR is something that is given to you, and there is one complicated expression. Okay. There is an expression for it, and then we also saw how that expression can be written as a sum. Okay. So loosely a sum because it is approximately a sum of several terms, and each term comes from one parity check. Okay. So each term coming from one parity check. Parity check involving the ith bit, right. So involving Ci. Okay. So of course this is not true in general. There are, I mean, you can add only when they are all independent. Okay. Each parity check will of course give you some information about the ith bit, but they are all not independent. Okay. So you have no business really adding them. You have to account for how they are dependent, but a good approximation, like I said, seems to be in practice that you can add them without worrying about any of these things. Okay. So that is the basic description I gave for the bitwise MAP decoder. None of this part was very rigorous. It was mostly heuristic. We were looking at it from simplifying the expression point of view. We saw mostly examples, some 2 or 3 examples, and some cases where it worked, some cases where it did not work. Okay. Of course there is lots of theory behind these things. Okay. And we do not have too much time to go into all those theory, but of course there is practice is what is most important, and we saw how you can do simulations to verify whether you are getting any kind of coding gain. We saw some pictures and some definitions of coding gain for classical codes, and we saw that there is a large gap from capacity. Okay. So one thing I want to alert you to, which I did not maybe pay too much attention last time, was the difference between bit error rate and block error rate. Okay. So when you do not do coding, you have to pretty much decode one bit at a time, and so your bit error rate, block error rate and all coincides because your block is simply one bit. Okay. It does not make any sense to do anything else, but when you do coding you will get a bit error rate, you will also get a block error rate, and both of these will not be the same, they will not be equal. In fact there are bounds relating the two, but usually the bit error rate will roughly be block error rate divided by something, right. So you have to think of there is some division by the number of bits per block going on there, and depending on how many bit errors you make for a given block error, the two things will be related in a non-trivial fashion. Okay. So you will get different kinds of curves, you have to pay attention to that. So normally as a metric we will be mostly interested in bit error rate or block error rate. What do you think is a good metric in practice? Bit error rate,
block error.
I do not know. So sometimes it depends on the application, but usually block error rate is the real gold standard, right. I mean you have to worry about entire frame being wrong, but then the other argument to that is maybe maybe your message is not very heavily compressed, so maybe your message is some big BMP file, right. In that case a few errors here and there does not really sacrifice on the quality of the final experience, but nevertheless it is important to know block error rate in most cases, okay. Particularly if you have a big communication system which has multiple layers. I mean, these days communication systems are built with layers, so the link layer is something which will have all these coding and all that. Above the link layer there will be some other layer which will only expect a certain block error rate, okay. So depending on block error rate, the efficiency of the higher layers will be disturbed, okay. So block error rate becomes quite crucial in practice, okay. So we have to next move towards low density parity check codes, but before that I want to quickly point out one thing which we missed when we looked at the soft ML decoder. So we are going to go back to the what is known as the union bound estimate. Estimate of what? Estimate of block error probability of, let us say, FER for soft ML decoding. Okay, so it is kind of a long title, but that is essentially what we are going to do next. Okay. So I was making this statement that ML and MAP decoders are quite complicated and you cannot do accurate analysis. Accurate analysis becomes difficult. For the repetition code it was easy. For even other codes there are too many correlations you are computing in soft ML and they are all dependent in a crazy way. You could do it, but it is very difficult to define those areas precisely and do that. Okay. So this is actually a recurring theme in many areas, not necessarily coding and decoding. In many communications, whenever you do soft decoding, accurate estimation of block error probability or frame error rate and all is very hard. Okay. So what most people resort to is some kind of a union bound estimate, and at the heart of the union bound estimate is something known as pairwise error probability. Okay. So it turns out in most cases you can always compute pairwise error probability very easily. Okay. And it's a very easy thing to compute. There are only, so it's like there are only two decisions, right. When you say pairwise error probability, you have only two hypotheses, either it is this or that. Okay. So those kind of regions are very easy to compute error probabilities for. When you have multiple code words and you can go wrong in multiple ways, then those regions will interact in strange ways and you can't compute exact errors. Okay. So let me begin by this description of what is pairwise error probability. You will see what I mean. Okay. So once again we are going to think of an NK code. Okay. NK code and over and I am going to use BPSK over AWG. Okay. Okay, same as before, nothing has changed there. And so suppose I transmit the setting for pairwise error probability is as follows. Okay, pairwise error probability, or abbreviated as PEP if you want. Okay, this is the setting for pairwise error probability. You transmit a particular code word. Okay, for the linear code case we can fix it to be the all 0 code word. Okay, so let us say we transmit some particular code word. This is the code word that is being transmitted. It gets converted into some symbol vector, noise gets added to it, and you get a received vector R, and the soft ML decoder is working on it. Okay, and it produces some C cap. Okay. So suppose let us say C prime is another code word. Okay. The pairwise error probability between C and C prime is basically the probability that C hat equals C prime. Okay. So given that C was transmitted, pairwise error probability between is probability that C cap equals C prime given that C was transmitted. Okay. All right. Is that okay? So that okay? You are staring at it like I have made a mistake. Yes.
Both combinations of some other code we are decoding.
What is the question? What is the error you are saying? So this is, I mean, probability that the soft ML decoder decodes to some other code word, C prime. C prime, sorry, C hat equals C prime, given C is transmitted. Okay. So here this probability, it turns out, is quite easy to evaluate. I will show you how to evaluate this. It's a very simple expression. It's just one Q function. Okay. So it might not seem like it at the outset, but it's a very simple one Q function. Okay. Again, the geometric view will help you here. Okay. So we have this big space of, let's say this is Rn. Okay, and you have S which was transmitted, and you have, let's say, another vector S prime, which is what, 1 minus 2 C prime. S is 1 minus 2 C. Okay. You transmitted S. Okay. What happens in this Rn? Z gets added to S and you get R. Okay. So some R you get here. Let's say you get an R here. Okay. This is S plus Z. Okay. The question I am asking essentially is, when will R be closer to S prime than it is to S? Okay. So essentially I am asking the question, when is this distance, let us say this is y, this is x, when is the y greater than s? This is essentially the same as probability that y is smaller than x, I am sorry. Okay. So what you can do for this is to look at this line which joins S and S prime, okay, and project what? So you basically you have to look at the projection of R on this line. Okay. So it is enough if you view that. Okay. So in fact the region will basically be the bisector of this line. Remember, this is all n dimension, so I can't just say bisector. Means there will be some n minus 1 dimensional object which separates these two things. Okay, huge thing right in the middle, and you have to only ask the question whether R is on this side or that side. So all you have to do is to look at the vector R minus S and project it onto this this line joining S and S prime and see if it has crossed half the distance. Okay. So you can also show that that projected point, okay, will basically be S plus Z prime, and the Z prime will also have the same, well, it is just so let me redo this carefully. Okay. So let me not say this. So this distance, okay, this distance on this line, it is just one value, it is not a vector anymore, it is just one value. This distance you can show is normal with what? Mean being 0 and variance is the same sigma square that you had for Z. Okay. So you would have a variance for sigma square Z, right? Let me make sure I have that right. Yeah, I think that is correct. Okay. So this distance would have, so basically what you have to do is, when you project R minus S onto this line, the projection of S will just basically bring it down to S. It is almost like S has become the origin. Okay. So and then only thing you are doing is you are projecting Z onto this. Okay. When you project Z onto something, and you can think of a unit vector there, and it is just when you multiply it with the unit vector, you will get one random variable with the same variance as sigma square. Okay. So you can show this, it is not too difficult. So it will be n by sigma square. Okay. So essentially this probability now becomes the same as probability that this distance, so to speak, okay, this distance from S is greater than S minus S prime by 2. Okay. So that is all that you have to worry about. Okay. So there is some normal distribution 0 sigma squared. When will that be greater than, did I make a mistake somewhere? Made a mistake.
Bounded by some.
Sorry, which distance? Yeah, that is S and S prime you mean. Yeah, that is the distance S minus S prime.
On that, how can we have a normal distribution?
You have to take the sign into
No. Let's repeat the question again.
Distance between S and S prime is going to be some finite.
No, it's okay. So there is no condition that the projection has to lie between S and S prime. It can be outside of S prime of that triangular source. So think of it as, so basically it's almost as if BPSK is happening over this huge dimension between S and S prime. Okay, so it's as good as that. Okay. So you have S, you have only one line to S prime. Okay, and any error that you take go in several other dimensions ultimately gets projected onto that one line. So it's almost like BPSK between S and S prime. Okay, so only the distance between S and S prime matters, and you have the same variance for that projection of any n dimensional normal operator also. You can show that, that's not very hard. See, projection will also be Gaussian, right? It's a linear combination of several Gaussian things. It has a unit norm, so you will get something similar to that. Okay. Anyway, so this is the answer.
the sign as to whether the.
That's why I put the norm between S and S prime. So this will be like the Euclidean distance, square root of the Euclidean distance between C and C prime, I mean S and S prime.
But then if you have the distance to the mean as 0,
You can't go negative side.
then how do you show the negative distance?
Yeah, it can be negative also. See, it's normal distributed with mean 0, variance sigma square. That normal distributed value can take negative value.
Yeah, so
Gaussian. So this distance I am saying is basically distributed as like this. So it can be both positive and negative.
So what does that negative
point
distance
is, say, falling outside?
Yeah, if it goes
S0?
negative, then you decide S.
yeah, that's
Yeah, it's like BPSK, right? So BPSK you transmit +1 and -1. If you get +2, you decide +1. So this distance, when I define, I will define as distance from this in this direction. So if it goes negative, it will be minus.
We'll extend the line.
Okay. Yeah, you have to extend the line on both sides. Okay, I did not expect this to be so controversial.
So you're taking distance with sign.
Yeah, it's with sign. Maybe I shouldn't have put both arrows. Okay, I should maybe get rid of this guy and put just this arrow in this direction. So if it goes to the other direction, I'll make it negative. Okay. So it's a clean. Believe me, it's a very clean idea. It's correct. Okay, so it's not wrong. It's a very simple thing. See, this is why essentially pairwise error probability is easy in many cases. Okay, so you have one point, you have another point, and there's a straight line joining these two, and you're just dealing with one dimensional stuff. Nothing happens beyond that. Okay. Of course, the projection can take you on this side. If it takes you to that side, you're definitely not going to make an error. It will be correct. It can also take you to the other side of S prime, and then you will definitely make an error. Okay, so it depends on the distribution. Is that okay? So, but only the projection matters. That's the thing you have to be convinced of. Okay, yes.
Can you reiterate the how you said that the distance would be the normal?
Okay, so when you do projections, so Z is going to be, so let's say Z is some, so this question is being asked, right? So basically if you do Z will be Z1, Z2, Zn, right? Each of these things is normal with mean 0 and variance sigma square. Okay, so when I project onto anything, I'll be taking a dot product with some unit vector. Okay, its norm is 1. Okay, so let's say the unit vector I picked is u1, u2, un. So the distance will essentially be summation ui zi. It has mean 0 and its variance is summation ui square, and that's 1. That's all. Is that okay? It will also be normal because it's a linear combination of a jointly Gaussian random variable random vector. Okay, all right. So we've gotten up to this this point, and this is normally distributed. So this simply becomes a Q function, Q of norm S minus. Let me write this carefully. Q of norm S minus. Okay, so for some reason. Okay, I think I should. Time has come to wipe the slate clean. I don't think the air conditioning is on. in spite of his assurances, I am definitely sure it is off. Okay, so let us say S minus S prime by 2 sigma. So it is as simple as that. Okay. Now what is S minus S prime? Let us look at S minus S prime a bit more closely. S minus S prime norm is square root of what? It is going to be summation. Okay, I drew a long square root, so let me write it down. S1 minus S2 S prime 1 squared plus S2 minus S2 prime squared plus so on till Sn minus Sn prime squared. Okay. So it turns out if you now know the Hamming distance between C and C prime, you can use that to write this precisely. Okay. So after all you are doing BPSK, so you know S1 and S1 prime for instance are plus 1 and minus 1s, and if the two code words did not differ in that first position, they will be 0, the difference will be 0. If it differs, it will be 2. Okay. So it will basically be 2 times the Hamming distance between C and C prime. Is that okay? Every time it differs, you get a 4 inside the square root. So you take the I mean every time it differs, you get a 4 inside the square root.
Yeah. So the 2 comes out.
2 root, oh the root, there is a root for the distance. I thought you meant there is a root for that. Is that fine? So this is what you would get for the S minus S prime. So essentially pairwise error probability between C and C prime simply becomes, so remember this is BPSK AWGN with minus 1 plus 1, if that minus 1 plus 1 is not there, there will be some nasty constants floating around it. Okay. So that does not change the final answer though, when you see the final answer, once I express it in terms of EB over N naught, final answer becomes exactly the same. Okay. So that is the idea. Q of what? Root of dh C comma C prime by sigma. Is that okay? So remember 1 by sigma, if I want to write it in terms of EB over N naught, EB over N naught for our case is what? Is 1 by 2R sigma squared. Okay. So R remember is K over N, so we will get an N over K there. So if you were to write it in terms of that, you will get some square root etc. in the inside. Okay. So you can express it in terms of that. Okay. But the next interesting thing is, suppose I want to write probability of error, okay, using pairwise error probability. Okay. Okay. Wow, people have some ready-made answers, but let me go through this a little bit more slowly. Okay. You can use something known as a union bound. Okay. So it turns out the idea you use there is the error event that you have. What is your error event? C not equal to C cap. Okay. You can write it as a union of all the C prime in C that is not equal to the transmitted code word C, C hat equal to C prime. Okay. Remember it is a union and it is not a disjoint union. Okay. It will not be a disjoint union, right. C prime C hat equal to C prime, we saw it was just on one dimension. If you go to another dimension, if you go back to this picture, if you go along some other direction to some other, let us say S double prime, and if you draw the bisector there, all these regions will overlap. Okay. So it is a proper union. Okay. It is not disjoint or anything. Okay. So you can't simplify it in any way you like. Okay. So you can only say that the probability of error here will be less than or equal to 2 power k minus 1, like they said, because there are 2 power k minus 1 here times the pairwise error probability. Okay. But if you do this 2 power k minus 1 and all that, you will not get anything reasonable. Okay. So it turns out the union bound estimate works very well if you restrict yourself only to closest code words. Okay. You can do that and it gives you a reasonably good estimate in many cases. Okay. So what do I mean by closest code words? The code has a certain minimum distance, right, some minimum distance d, let us say the code has a minimum distance d, you only have to look at those events which are very likely to have happened, okay, which means you only have to look at those code words which are at distance d from my transmitted code word, okay, and I will take a union only over that, okay, and then do a union bound with that, okay. So, it is clearly not the complete error event, so only something like a closest code word error event, okay. So, you define some other error event which is maybe some, I will simply call it error again, but remember this is not the same error as before, okay. This one is C hat, distance between C hat and C is equal to D, where D is the minimum distance of the code, okay. Okay. So, this error event is simply union over what? C prime in C such that the distance between C prime and C is exactly equal to D, okay, and then you simply take the same event C hat equal to C prime, okay. So, maybe here I will put less than or equal to D, okay, just to say that these are the code words within D. I only have to look at those code words which are exactly at distance D, because I know my code's minimum distance is D. So, there is nothing else in between 0 and D, okay. You have to make go D distance away, okay. So, here once again when you compute this probability of error, you cannot do exact computation, you have to once again do the union bound, but then you get a much better factor multiplying it. It is not 2 per k minus 1, all the code words are not going to be at a distance D away, okay. Maybe I will denote that by AD. AD is the number of such C prime, okay. You can show that this AD will be independent of C for a linear code. Any C you take, you will have the same number of code words at a particular distance away from it, okay. So, it is very easy to show that, okay, for a linear code this will be true. So, I do not have to qualify it with C, it is just AD, it is enough, okay, times the pairwise error probability at a distance D. What is the pairwise error probability at a distance D? Square root of D divided by sigma, okay. So, this guy is usually called the union bound estimate, and it is a pretty good estimate for the soft ML decoder, okay. So, it is okay, it gives you a nice nice comparison of the various parameters here, alright. So, the union bound estimate I will abbreviate as UBE. So, let us do this UBE a little bit more in standard notation. See, this is basically AD times Q of square root of D times 1 over sigma, which I know is square root of 2 times n by k. Did I get that right? K by n, is it? Let me just keep it in terms of R, 2R EB over N naught. Am I right? Okay, so, this is square root of 2R EB over N naught. Let us write this as AD times Q of root of D times R. What is D times R? dk by N times square root of 2 EB over N naught. Okay, why did I split it like this?
BPSK in coding gain
DK
over BPSK.
This
the
guy is
code.
the only thing that will show up for the
BPSK.
uncoded case. If you do not do any coding, what you will get is simply square root of 2 EB over N naught, okay. So, if you do coding, that square root, that what is inside the square root 2 EB over N naught gets multiplied by dk by N. So, roughly the coding gain according to the union bound estimate is simply dk by N, okay. So, from here you can read off that the coding gain is dk by N, okay. Right? Yes or no? Think about it. Okay. So, this guy simply becomes the coding gain according to the union bound estimate, very rough estimate, but nevertheless it is a good thing to have, okay. What it particularly brings out in my opinion at least is, it brings out the ultimate dependence on minimum distance. Okay, you can go to BPSK AWGN, you can do the best possible soft decoder. I was commenting that actually the soft ML decoder does not have an error correcting capability in the way we defined for the BSC. Okay, but that does not mean minimum distance is not important. Okay, minimum distance is ultimately definitely important, and even in the union bound estimate it plays a direct role in determining the coding gain. Okay, all right. So that plays interesting. I am sorry. Can it be greater than? I think there are bounds. No, see, d is less than or equal to n minus k plus 1. So yeah, I think 1 minus r. So yeah, so I don't know if it can be greater than 1 or less than. You have to look at it. You have to look at it. So yeah, you have to look at it. So what's crucial here once again is usually if you fix usually k by n will be fixed when you go to when you go to larger and larger block length. You want to go. I'm sorry.
It will become as 1 minus k minus 1 by n. So it's always something like 1 minus something.
Okay, so it's less than 1.
So square root of that will be greater than. Yeah, considering that.
Okay, so anyway, there's some discussion about dk by n, what it can be. It's not so important, well it is important, but see, let me point out something else here which might also be interesting. So you cannot ignore AD, for instance. Okay, so if AD is really large, okay, then it can play a role. Okay, it can play a role, and the way you have to read these expressions is to think of keeping k by n fixed and then going to larger and larger n. Okay, so that makes sense in practice. You know, I mean, you have a fixed rate. The rate is maybe controlled by several other things, you can't change that, and then you want to go to larger and larger block lengths. When basically try and use better and better codes. We know when you go to large block length, codes become better, etc., right? Use better and better codes, right? And then what kind of coding gain will you get can be a question that you can ask. Okay, so for instance, as you go to larger and larger n, your AD will also keep increasing as a function of n. Okay, so if AD is really large, it's increasing very large, very quickly as a function of n, then also you will be in trouble. Okay, so that's also nicely brought out by this union bound. Okay, what matters is d controls a lot of the gain, but also AD matters. If you have too many code words nearby, somehow you will make an error somewhere. Okay, so it's good not to have too many code words at the minimum distance also. Okay, so even that plays a fairly critical role here. Okay, anyway, so this is the union bound estimate, and this is pretty much as far as I can recall, pretty much the only analysis you can do for soft ML decoders. It's very difficult to do any other kind of analysis. Okay, so this is an important breaking point in the course, as in we are stopping at a critical point. We are going to do a major change of course beginning in the next from the next few minutes onwards. Okay, so this is a stopping point for soft decoding. Okay, coded modulation and soft decoding. How do you combine codes with a simple modulation scheme like BPSK? Of course, if you have a more complicated modulation scheme like 16 QAM, things become a little bit more complicated. Okay, but ultimately what matters is how you can compute log likelihood ratio. Okay, that's the only thing that matters. Okay, you might have a 16 QAM constellation, but it doesn't matter. Each constellation point corresponds to 4 bits. Given that you received a particular value, how do you compute log likelihood ratios for each of those bits? As long as you can compute log likelihood ratios, you can go into your soft decoder and decode. Okay, so technically at least there is no significant challenge in going from BPSK to 16 QAM as far as decoding is concerned. Find the LLR and then you decode. So there is no big deal, no confusion. Okay, so that's why BPSK is kind of enough for a first course. You understand BPSK, you can understand other things also. Okay, so the main themes were there are optimal soft decoders, but in most cases they become very tough to implement. Okay, the trick is to understand them, understand their expression, and see how they can be simplified. And it turns out this bitwise MAP decoder has a particularly nice way of simplifying into something nice based on parity checks. Go one parity check after the other, it seems like it can simplify. Okay, so that kind of decoding is, like I mentioned, is used a lot in this low density parity check codes, and that is what we are going to start now. Okay. So, if you have any question on this, now is a good time to maybe bring it up. If there is any comments on anything we saw on the soft decoding part, because this part is something that I can actually ask questions in the exams. So, once you go to LDPC codes, it is really hard to ask questions on those things. So, this might be a very good point for for the end semester exam, yeah, maybe. Okay, so please make a note of this. All right, so we are going to move to low density parity check codes. Okay, so the abbreviation is LDPC. Okay, some people who are very grammatically correct and like good grammar will put hyphens here. Okay, so if you are like me, and if you are like me, then you will put hyphens in some places and you won't put hyphens in other places. It's okay. I think anything is fine. Okay, so these codes were actually invented by Robert Gallagher, or Bob Gallagher as is popularly known, in his PhD thesis. Okay. Guess when? Okay. 60s. Okay, let me just say early 60s. Okay, I don't know the exact year. Okay, so it was born in his PhD thesis in the early 60s, and because of various technological limitations and implementation, etc., these codes were not, people did not look at it for a long time, and now of course they are making their way into many standards, okay, wireless, otherwise. I mean, every standard pretty much these days, at least there is one proposal for LDPC codes in many of these standards. Okay, so get into some, they may not get into others, but these are very popular codes today. Okay, so the definition is so simple that I could have made it even in like second or third class that we had. Okay, we do not have to wait for so long to define low density parity check codes. Okay, so it is very easy. The definition is basically a linear code with a what is known as a sparse parity check matrix. Okay, what do I mean by sparse? Very few ones. Okay, so very few ones. Okay, so this notion of sparse is also basically low density, right? So the density of ones, you can define density of ones if you like very rigorously. You can say number of ones divided by number of rows times number of columns, and that has to be low as in smaller than 1, much smaller than 1. Okay, so you can define all these things rigorously, but I guess the idea is basically sparse. Okay, so this is the main idea, and this is a linear code. So, well, the definition is not restrictive at all. I mean, it's not, doesn't say what is a code. I mean, if you compare this with the definition of a Reed-Solomon code, I wrote down a very precise parity check matrix. You might say, okay, what is alpha? We don't know what alpha is still, but whatever alpha is, it's a very precise, well-defined quantity in some finite field, and there is a very precise parity check matrix. Okay, so here is a definition which is totally, I mean, totally open. Okay, anything can be a low density parity check code, it looks like. Okay, so somebody specifies a code. How do you know if it's a low density parity check code or not? I mean, it's tough to find out, right? How do you know if it has a sparse parity check matrix or not? Remember, sparse parity check matrix means, see, each row of the parity check matrix is a code word of the dual. When I say sparse, I want very few ones. Okay, so if I want a low density parity check matrix, I have to find low weight code words of a code, right? Maybe the dual code in this case, but you have to find the low weight code words of a code. Okay, like I said long time back, finding low weight code words is a hard problem. It's not very easy given a parity check matrix. So you can't even be very sure if a given code is a low density parity check code or not. Okay, so that kind of a definition it is. So the only thing you can do is the opposite. You construct a parity check matrix which is already low density. Okay, so you put very few ones into your parity check matrix. Okay, that's what is usually followed. okay. So that is what is implied by this. But another thing you will see as we go along is we will not really worry about minimum distance or trying to prove minimum distance. We will be concerned about it in the construction, we will take care of it in a different way, but that will not be the explicit worry, okay. So most, if you remember the Reed-Solomon construction, we were very worried about error correcting capability, okay. How do you correct a given number of errors, okay, how do you construct a parity check matrix where a given number of errors can be corrected. Here that will not be the point, we will just construct it, we will try and decode, come up with a decoder, we will decode, and the way we will evaluate the decoder will basically be by simulations pretty much. There is some analysis which I will also touch upon, but mostly it is done by simulations, okay. So that is how it will work. So in many ways this will be very different from the way I treated Reed-Solomon codes, okay. And you will see the closest connection that can be made in terms of motivation, okay. So even though this was born in a completely different context, when you introduce it in a course, you want to kind of make it fit with something else, right. You want to say, okay, all this happened, so because of that this is great. The best way to tie it up with that is maybe the bitwise MAP decoder, okay, and the way we split it up in terms of parity check matrices. And you remember I made an argument saying low weight parity checks are good for you, in the way you split it up, okay. And then another motivation for the sparseness is, suppose I take two parity checks that are very sparse, it is very likely that they do not overlap, they do not have anything in common, which means the extrinsic information that they give you is going to be independent. So you can keep on adding more and more very easily, okay. So and if you have them explicitly in your parity check matrix, you have a good starting point, okay. So that is the idea, that is what kind of makes sense at the end, okay. But of course this is not how it started, but we can justify the popularity or the reason why it becomes so nice by all these other connections with the bitwise MAP decoder and motivations from that, okay. Anyway, so this is a general definition. There are specific classes of LDPC codes that are much more, that are actually popular, okay. So which are a bit more specific, you can actually construct them, but still not totally specific, as in they will not specify a single parity check, but at least there will be a class or ensemble of parity checks which will behave in the same way according to some definitions, okay. So that is the definition we are going to do now. The first class is a so called regular LDPC class, okay. So in fact Gallagher in his thesis introduced only regular LDPC codes, he did not introduce the other kinds of LDPC codes. What will be the other kind of LDPC codes that are not regular? Irregular LDPC codes. In fact regular LDPC codes are a special case of irregular LDPC. So you cannot say that they are another bigger class. So what is regular LDPC code? So you say sparse for LDPC, and then you have to say constant column weight and constant row weight. Okay, so maybe we will call this WC and a constant row weight. These are the two things that define regular LDPC codes. Okay. Okay. So LDPC codes are codes which have a sparse parity check matrix. Regular LDPC codes are those codes which have a sparse parity check matrix, it is also there, and then every column should have the same weight, as in the same number of ones. Every row should also have some other same weight, okay. So same number of ones, so WC and WR, okay. So you can now define what is known as a N, WC, WR regular ensemble of LDPC codes. Okay, I can call it set, but ensemble sounds a little bit more grand expression, okay. So it's good to use these terms, okay. So what are these codes, okay. Number of columns equals, okay. So these are basically parity check matrices that have the following properties: number of columns equals n, number of ones in each column equals WC, number of ones in each row equals WR. Okay. What about number of rows? Should I specify that? It turns out that is not independently specified. Okay. So, once you have n WC and WR, the number of rows becomes, what does the number of rows become? How do you do it? You have to compute the number of ones in two ways, compute them column wise and compute them row wise. You have to of course get the same number. So, you equate that, you will get that the number of rows becomes n times WC by WR, okay, and this has to be of course an integer. So, that will impose some restrictions on n for a given WC and WR. Okay. So, is that clear? How did the number of rows become n times WC divided by WR? Okay, think of the total number of ones in the entire matrix. It is definitely equal to n times WC, and it is also equal to number of rows times WR. So, that equation gives you number of rows as n times WC by WR. Okay, and this has to be an integer, right? Of course, if everything has to work out, this has to be an integer. So, WR has to divide n times WC. So, that has to be a condition that is satisfied, otherwise you cannot have an n WC WR regular ensemble. Okay. Okay. So, the next question which is interesting is, how many such matrices are there for a given n WC and WR? How many such matrices do you think are there? Very many. That's the answer I wanted. I didn't want a very precise answer. There are quite a few, right? It's not one, definitely not one. There are lots of matrices. In fact, as you increase n, if you keep WC and WR fixed and increase n, okay, so that's what you might want to do, right? See, remember, I want a sparse matrix. So, usually what people do when they look at these parameters is, usually you fix WC and WR as some constant, as constants, okay, and then you look at this ensemble for increasing values of n. Okay, remember, when you go to larger and larger n, I expect better and better codes, right? So, larger n means better codes. So, I want to increase n. Okay. So, as you increase n, the number of codes, number of such matrices is going to be too many. Okay, there are going to be lots of codes. Okay, that is the first point. Then why do we consider all of them to be in one ensemble? Okay, of course, there has to be something that follows which makes sense. It turns out there is a decoder, and when you run the decoder on any one code in the ensemble, you are very likely to get very similar answers as when you run the same decoder on any other code in the ensemble. So, all these codes in this ensemble give similar performance when decoded according to some specific decoder. Okay, that is the reason why you want to think of all of them together. Okay, so in fact, this WC and WR controls the performance of that decoder, which I have not yet described. So, eventually we will see that is the motivation for thinking of all these codes together as one. Okay. So, before that, what about the rate of this code? Rate is what? It is actually n minus rank of the matrix of the parity check matrix, am I right, divided by n. This is the actual thing, but what do I know about rank of the parity check matrix? I can't really exactly calculate it. Okay, depending on where the ones go, I might have to do it, but I can definitely lower bound it. The rank will definitely be less than or equal to the number of rows. Okay. So, this n minus rank will be greater than or equal to n minus the number of rows, which is n WC by WR divided by n. So, this becomes 1 minus WC by WR. Okay. So, this quantity is defined to be what is known as the design rate. Okay. It is called the design rate. So, given the WC and WR, I know my rate is at least 1 minus WC by WR. Okay. So, at least one thing we know. Okay. So, all the matrices in this ensemble have a common lower bound for the rate. Okay. Rate is at least this for all the codes in the ensemble. Okay. At least that is one good starting point, much more definite. Okay. But the decoder also, like I said, behaves very similarly. So, that is the main reason for this definition. Okay. All right. So, the next interesting thing is construction. Suppose I give you WC and WR and give you an N. Okay. How can you go about constructing, let us say, one parity check matrix from this big ensemble? How will you construct it? Okay. So, Gallagher gave a solution for that, and that is called Gallaghers construction. Okay. And it works when WR divides N. Okay. It works when WR itself divides N. Okay. So, remember we wanted WR to divide N times WC. Okay. So, of course, if WR divides N, it will also divide N times WC. So, Gallaghers construction works when WR divides N. Okay. So, the construction is very simple, it works like this. Okay. So, you construct the overall parity check edge, okay, using WC submatrices. So, you will have a H1, then you have an H2, all the way down to the last one, which is HWC. Okay. So, the H1 part of it will be very simple. So, what you will do is, so each guy, the number of rows I have to tell you, will basically be the number of rows in each one will be N by WR. So, on to the last one, which is also N by WR. Of course, this drawing is not to scale. So, you have to imagine that all these arrows equal lengths. Okay. So, N by WR. Okay. And then I am going to put in the first row of H1, I am going to put WC once. Did I get that right? WR once, I am sorry. Okay. I am going to put WR once. Okay. What will I do in the second row? Okay, just start from here, WR plus 1 to 2 WR. Okay, so this guy is 1 to WR, this guy is all the way to 2 WR. Okay. This way, if you keep on coming, what will be the last thing here? It will go all the way down. Okay, the remaining things you put as 0. Okay. So, is that okay? Did everything work out correctly? Somebody is mentally checking, I think, N by WR, if I put WR once, will I get the correct answer? Yeah, I think it is okay. Okay, this works out. So, for H2, what you should do is, you take some permutation of, column permutation of H1. Okay. You do the same thing for H3, same thing for all the way down to HWC. Okay. So, this was Gallaghers construction, and clearly you can see it is not a unique parity check matrix, right. How many possible constructions are there? Okay. So, for H2 you have n factorial possibilities, H3 you have another n factorial possibilities. So, clearly it is going to be n factorial raised to the power WC minus 1. Okay. So, it has a lot of matrices and you can't even be sure which of them will actually generate distinct codes. Okay. So, right, you have to be careful, you can't just mix up the permutations, you might get the same code. Okay. So, there are a lot of codes and some of them will be distinct, some of them will be the same, etc., etc. Okay. So, this is Gallaghers construction and it is clearly an ensemble of several codes, not just one code. Okay. Even within Gallaghers construction it is a big set. Okay. For every permutation you pick, you get a different code. Okay. That is it, that is the construction. Okay. There is nothing more to it. Okay. Do not need to know any major finite fields and polynomials and everything, you can just construct, you can, it is almost trivial to write a MATLAB program for this construction. Okay. MATLAB has permutations, MATLAB has matrices, sparse matrices, you just write it down, you get a quick construction for Gallaghers construction. Okay. So, typical choices what people do, like I said, is to fix WC and WR for a particular rate and then look at larger and larger n. Okay. So, if you want to look at some simple examples, okay, you might want to say have a design rate of, let us say 1 by 2, okay, so it is kind of a canonical rate 1/2. So, I know I want this to be equal to 1 minus WC by WR. Okay. So, this clearly imposes the constraint that WR is 2 times WC. Okay. So, once you have a rate, WC and WR are related by that rate. Okay. And a very typical choice for WC is to simply take say 2 or 3 or something, very low number, right. So, a good choice for WC is 3, 2 turns out is usually not a good choice. So, you start with 3. Okay. So, 3 means you have WR equals 6. Okay. So, you can think of for design rate half n 3 6 regular LDPC ensembles. Okay. So, you know n has to be an even number, right, otherwise this will not work out. Okay. So, of course, I mean that's okay, there are enough even numbers out there, so you can just think of n as being n, it is not a big problem. Okay. So, n 3 6. Okay. Another choice would be to take WC equals 4. If you take WC is 4, then WR becomes 8, then you have the n comma 4 comma 8 regular ensemble. Okay. And for any value of n, you can think of larger and larger constructions that will work out. Okay. All right. So, of course, the important question is, out of all these random constructions, is there any one that is preferred? Okay. Is there any one that you would prefer for whatever reason? Okay. So, one reason might be you want a good minimum distance, another reason might be you want a very simple implementation of the decoder. Okay. So, there are so many other reasons that you bring in to choose a specific instance of this construction. You might want to do that, and that is what people do when they propose codes for the standards. Okay. They will propose a certain code and say this performs really well. Okay. So, it also has maybe a good minimum distance, it has a simple implementation of the decoder. Okay. And the main criteria is going to be, of course, coding gain. Okay. What is the coding gain corresponding to a particular construction? Okay. So, it turns out it is a bit difficult to quantify these things exactly. Okay. At least for a finite n, if you fix everything and say I give you a certain construction, a particular permutation for H2, particular permutation for HWC, you tell me what the coding gain is for your favorite decoder. Okay. Like I said, the best thing to do is to simulate and try. Now, each of these simulations is going to take a long time. Remember, you want to simulate down to 10 power minus 6, which means you have to simulate 10 power 8 blocks. Okay. And if you want to try each and every one of these codes, there are too many of them, and you will not finish before the earth dies or something like that. I mean, there may not be any point in doing the communication at all. Okay. So, what you really want is some guideline, right. What is a good guideline to look for? What are the good choices for WC and WR? Should I pick 3,6 or 4,8, right, which is better for design rate half? That is the question that you might want to answer. Okay. And given all these complexities, given that you are not able to answer all these things very precisely, we will settle for any guideline or some approximate analysis which leads us to a good choice. Okay. Of course, it has to be backed up by simulations, but it need not be very rigorous. Okay. So, many of the analysis I will do for LDPC codes, at least you will see it is not very rigorous. Okay. It will be some kind of an approximate analysis which will be maybe backed up by simulations, and that is good enough. and in most cases people will do also not just approximate, but also asymptotic. What is asymptotic now? As n becomes, well, infinite, okay, so very large. Okay. So, we will do what is known as approximate asymptotic analysis for LDPC codes, and that will give us very nice design choices which you can definitely use in finite time, okay, without worrying about which is also quite complicated actually. If you want to program all those choices in, it is quite complicated by itself, but at least it will run in our standard computers, okay. So, it will work very fast and you can do it, okay. And this is of course, like I pointed out, very different from Reed-Solomon codes or anything, which came very nicely, and there was no doubt about that, okay. So, of course, everything hinges on the decoder, and before we go to the decoder, let us see one more construction, okay. So, you might say this WCWR works only for some n, what about all n? If it does not work, WR dividing n may not hold for you, okay. So, how do you do that? And there is one more construction which is called as the socket construction, which you can say is due to Urbanke and Richardson. It is much more recent, okay. And this I will describe using a representation of the parity check matrix, which is called as the Tanner graph, okay. So, this Tanner graph is quite important. I am introducing it in the context of the socket construction, but it is interesting in its own regard for various reasons, okay. So, it is basically a graphical representation of a parity check matrix, okay. So, when I say graph, it's not your xy axis graph with log scale or something. It's basically what, I'm sorry, vertices and nodes. It's a graph theoretic graph, okay. So, it's not any of your other graphs, okay. So, you will have vertices and edges connecting them, okay. So, that is the graph I am talking about here, okay. So, best way to define a Tanner graph is by example. You will see it is a very easy thing to define, and it has a very nice generalization, very easy generalization. So, I do not have to define it in the general case. So, let me define it by example. I will take a simple parity check matrix and show you the Tanner graph corresponding to that, okay. So, let us say we take 1 0 1 0 1 0 1 1 0 1 1 0 1 0, okay. So, this is my parity check matrix, okay. It has regular row weight, but not really a regular column weight, but it does not matter, okay. So, Tanner graph is basically a bipartite graph. A bipartite graph will basically have one set of columns on the left side and one set of vertices on the left side, another set of vertices on the right side, and all edges will connect from left to right only. So, all vertices on the left side will not have any edges between them, it will only be from left to right, okay. So, these vertices on the left will correspond to the columns of this parity check matrix or the bits of the code. Remember, the columns of the parity check matrix also correspond to the bits of the code, right. So, I can think of, you remember there was always this way in which we wrote down the code words of the code on top of the columns, okay, that made some sense. So, here we have 5 columns. So, I will have 5 left vertices, okay, and we have 3 rows, we will have 3 right vertices, okay. The right vertices will correspond to the rows, okay. So, left vertices correspond to the columns. So, of course, the right vertices have to correspond to the rows, right. So, otherwise it will not work, okay. And the right vertices, just to distinguish them, I will draw them as squares, okay, all right. So, these are the left vertices, they correspond to bits or the columns. The right vertices correspond to the parity checks, right. Each row of the parity check matrix is actually a parity check, right, and they correspond to the checks or the rows. Okay, so the left nodes are also called bit nodes, the right nodes are also called check nodes. Okay, so you can call them column nodes, row nodes if you like. In fact, they are also called variable nodes, check nodes. So many names, as many names as there are researchers in this area, you can call them. Okay. All right. So now connections. Let's see if this is a very intuitive concept without even telling you what the connections are. If you know it, don't answer this question. Okay. So if you don't know, if you have never heard this word tanagraph before, how can I connect vertices on the left with vertices on the right? Okay, so basically it will depend on the locations of the ones. Okay, so wherever there is a 1, I should have some edge connecting that corresponding column and row. That seems like an intuitive way of doing it, and that's the definition of the column of the tanagraph. Okay, so if you want to draw that, you can look at the first column. It's connected to the first row and the third row. Okay, so you can draw a line like this. You can also do it the opposite way. So if you look at the first check or the first row, it's connected to the first column, third column and the fifth column. If I look at the second check, it's connected to the second column, third column and the fourth column. If I look at the third check, it's connected to the first column, second column and the fourth column. That's it, that's your tanagraph. Okay. So clearly there is a one-to-one correspondence between the tanagraph and the parity check matrix. Given a parity check matrix, you can go to the tanagraph. Given a tanagraph, you can go to a unique parity check matrix. There is no doubt about it. By the way, the Tanner stands for what? It's the name of a person. Okay, so don't think anything else. It's is this still an active researcher? I mean, it's quite an active researcher. Is this in UIC, if I'm not wrong, University of Illinois, Chicago. Okay. Okay, so these graphs were of course invented by him, so that's why it's called tanagraph. Yes.
We have a lot of ones basically.
Oh, you're saying it's not sparse.
Yes.
So tanagraph is not necessarily for a sparse parity check. For any parity check. Okay, so he's upset with the density. Said low density all along and suddenly I give you a high density matrix. So this definition holds for any parity check matrix. Of course, we'll work with low density, but it can be fused. Is that clear? This is a very simple thing, and like I said, the generalization is obvious. I mean, if you have any other parity check matrix, the tanagraph can be done very similarly. There's no problem. Okay. So how does the socket construction work? Okay. So remember in a n comma w c w r regular LDPC code ensemble, you have n columns and n WC by WR rows. Okay. So any parity check matrix in this ensemble will have a corresponding tanagraph, and it will have n bit nodes and n WC by WR check nodes. Okay. So let's draw them. So by the way, the socket construction will construct a tanagraph, not a parity check matrix, but of course you know how to go from a tanagraph to a parity check matrix. Okay, so you have n of them here, you have n WC by WR of them here. You imagine now that there are WC sockets in each bit node. Okay, you know that each bit node is connected to WC check nodes. So let's imagine that each of those edges go into some socket, and you have explicitly WC sockets. Okay, so you have WC sockets. Okay, so these are sockets. So these are basically locations for the edges to come out of. Okay. Likewise, on each check node you will have WR sockets. Okay. So, how many sockets will you have in total on the left hand side? How many sockets will you have on the right hand side? Okay. So, both of them will be the same. Okay. Number of sockets on each side. Okay. So, it is not both sides, n times WC. Okay. So, you number the sockets on the left hand side starting from the top 1 to NWC. Okay. So, you number them, number the sockets 1, this will be WC, this will be WC plus 1, right, all the way down to NWC. Likewise, here also you number the sockets PWR all the way down to n times WC. Is that okay? You number the sockets on both sides, and then you come up with pi, which is an arbitrary permutation of this set 1 2 all the way to n times WC. Okay. So, pi is some permutation of this. Okay. So, pi, what do we mean by permutation? Pi is some mapping from some 1 to 1 mapping from 1 to NWC to the same set. So, it is a 1 to 1 mapping. So, it is permutation. So, this will basically take an I to a pi of I. Okay. So, given any I will go to a pi of I. Okay. So, for any permutation I will take the ith socket on the left hand side and connect it to the pi of ith socket on the right hand side. Okay. Connect on left to pi of ith socket on right. Okay. So, every permutation will correspond to a Tanner graph, but there is one catch here which is slightly, which I have not explicitly pointed it out. Let me see if anybody notices that. What can happen? You can have multiple edges. Okay. So, that is the only problem, right. In this socket construction, it seems like you can have multiple edges between a single bit node and exactly another check node. Okay. So, you have some way, you need some way of handling that. Okay. Okay. So, what you can do, for instance, is what? Simply throw away multiple edges. If there are multiple edges, you just reduce the edges from there, but then what will happen? Then the weight will fall, you will not get a regular matrix. Okay. So, the socket construction produces regular Tanner graphs and not necessarily regular parity check matrices. The only problem is because of the multiple edges. Okay. But of course, it will also produce all the regular matrices will also be produced. There will be some permutation which will only give you there will be lots of permutations which will not give you any multiple edges. All those guys will give you a proper valid parity check matrix, there is no problem there, but it will also produce some other things with multiple edges, and if you want you can throw them away, or you could have some other way of converting it into some parity check matrix. But then in the socket construction you have to think of the ensemble in terms of the Tanner graph and not in terms of the parity check matrix. Okay. So, we have run out of time. I think, I do not know when we ran out of time, but anyway it is end of this class. So, we will stop here and pick up from here next week.